Alex Meyer, because we don't have a microphone and it's being live streamed so people can hear what I'm saying when I introduce Alex. So we're very, very happy to have Alex here from Michigan. Alex Meyer is a Charles and Patricia Nelson Presidential Professor of Environmental Engineering and founding director of the Center for Water and Society at Michigan Technological University, where he has been since 1991. He was their first director for 8 years, I understand. Dr. Meyer's teaching and research focuses on water resources sustainability, watershed processes, modeling, and groundwater flows, transport, and remediation. And he works on the Great Lakes, and that's also what he's going to talk about today, and among others also the Rio Grande, among other locations in the world. He's co-authored more than 100 papers. He has an engineering background, and I think it's fair to say for me that I think he's one of the first engineers that I have ever met who does much more with economics than typically is the case. He does not only just calculate engineering costs of new technology, for example, but he's actually working with an economic model to look at the economic values generated by the Great Lakes. So the topic of today's talk is developing the Great Lakes blue economy, water productivity, water depletion, and virtual trade in the Great Lakes Basin. Please join me in welcoming Dr. Alex Meyer.
Thank you. Thank you. Thank you, Roy, for inviting me. Also, thank you for reading the correct title. I'm sorry, this title slide is from another talk. It's the talk I'm supposed to give today, I think. So I'd like to start out first by acknowledging my collaborators in this work, Ben Riddell from Arizona State University and Stanley Mubako from the University of Texas, El Paso, and several undergraduate research assistants, and also our funding came from the Great Lakes Protection Fund and the National Science Foundation. And the work I'm going to talk to you about today has been published in the AGU journal Earth's Future, if you'd like to see more details. And this work combines several different sorts of data streams to be able to come up with these virtual water trade exports and imports within the US portion of the Great Lakes, and I'll explain to you what all that means as we go along. I hope this isn't offensive to anybody except the guy with the orange hair. But thank you for letting me in. I don't know if I'll be returning, so thank you for not building the wall yet so I could come today. I'd like to just make sure we're all on the same page in terms of what we mean by virtual water. So we can define, first thing we have to do is to define the region over which we're doing our virtual water calculations. So let's say we have a watershed. And then looking first at virtual water exports. The virtual water exports would be the water that is consumptively used within the basin to make a product, a crop, a commodity of some kind, even a service. And then that product is exported out of the watershed. And so we say that the water used to produce that is virtually being exported out of the watershed with it. And then virtual water imports, of course, would be the reverse, that we import goods and services into the watershed. Wherever those materials came from, water was used to create those, and so we are virtually importing water through things we're importing via trade into the watershed. And then within the watershed, depending on the scale, we can have substantial amounts of recycling going on, where we're producing things. Water is being consumed by producing those things, but then they're consumed within the same watershed. And so usually we say that those things cancel each other out so that the internal virtual water imports and exports end up just going to zero. And so overall then our net water balance would consist of the virtual water exports minus the imports. And then we have those internal exports and imports, which again cancel each other out. So this is just the broad start here. And by the way, I encourage you to ask me questions as I go along if you need anything specified better or have a comment. So please do interrupt. So why study virtual water trading? So my first bullet here, I think, is probably obvious to everybody in the room that our water resources are subjected to increasing pressures from various aspects of global change. And then thinking further, then trade links the productivity and resources of regions across the world. And those trade routes provide conduits for moving water virtually in and out of a particular region. Sometimes you might see that more water is being virtually exported out of a water-stressed region into a region where that is not water-stressed, where water is plenty. And so from a sustainability perspective, that doesn't make much sense to be exporting from water-scarce regions into water-rich regions. And the literature on virtual water trade has grown since the early 1990s, when Allen may have been the first person to coin the term, although there are people arguing about that now. And much of the work that's happened since then, the work on water footprints or virtual water trade, is for specific goods or services for either very small regions or larger scale, like the national scale. And then these imports and exports are considered, but they're not considered against water availability. So we don't really have a way to measure how much these imports or exports are potentially impacting water availability within a region. So in our work, we want to look at a wide range of trade sectors. We're looking at a wide range of scales, and we also want to look at these imports and exports against water availability. So this is our study area. It's just the US portion of the Great Lakes. I'm sorry to show yet another map where Canada is just a blank. But this is a data availability problem. We knew where to get data on the economic portion of the work and also on the water consumption of the work. But I would certainly be happy to extend this to the rest of the basin. So we looked at 213 counties in the US portion of the Great Lakes Basin, except Illinois. Illinois is very complicated when you look at water moving in and out. Only really Chicago is in the basin, Chicago and some suburbs, and it's just too complicated to study. So why study virtual water trade in this Great Lakes context? This concept of blue economy, which is in the title of the talk, and it is something I know Roy is very interested in, is gaining popularity in the Great Lakes region. And depending on who you talk to, they will define blue economy in a different way. But very generally, I think what most people think when they're saying blue economy is that can we use the abundant water in the basin to fuel an economic revival? So at least on the US side of the Great Lakes Basin, this is where you find a lot of these old industrial Midwest cities where manufacturing has gone away, and there's a struggle to recapture the economy in those places. And so people say, we have all this water around, can we put it to some use that would help our economy? We know that stress on surface water and groundwater resources are already present in this region, which is supposed to be the most water-rich region perhaps in the world, freshwater-rich region in the world. We also know that the Great Lakes Basin is very important to our two nations' economy, and yet this virtual water framework has not been applied to the basin except for a very limited study a year or so ago. Our focus here, when we look at consumptive use of water, is on surface water and surface water in the tributaries. We're not considering directly the Great Lakes themselves. Indirectly, we're considering groundwater, and you'll see how that comes in as it relates to surface water. But the motivation for looking specifically at surface water, by this I mean inland streams and lakes, is motivated because there are ecological limits being placed on withdrawals from these tributary watersheds. And they're now policy, and much of this has been motivated by the Great Lakes Compact and Agreement, which was signed in 2009. So by ecological thresholds, I mean in Michigan, for example, where I come from, almost all the rivers and streams have been designated in terms of the allowable stream depletion. So for example, they're designated by their size and their temperature. So a cool, transitional, small stream has a very rigid regulation on it now as to how much water can be withdrawn from that stream. So only 10%, for example, only 10% during a low flow month can be taken from these cool transitional streams. That's partially because those streams have lobbyists. So we kind of joke that in Michigan we have these small, cool streams where the depletion limit is very small. And then we have these big, warm rivers where, sure, take almost as much as you want. This is a little bit of an exaggeration. So in the small streams, we have trout. In the large streams, we have fish that nobody seems to care about. So the trout lobby, as I like to call them, very important allies, but we're very instrumental at putting these stream depletion limits in. Now, when we look at stream depletions, we need to be careful in terms of our accounting, because it's not just about the water that's withdrawn directly from the streams, but groundwater can affect stream depletions too, as I'll show you in a moment. And we also need to consider return flows. So I divide up withdrawals or water use into consumptive use and return flows. Consumptive use would be water that is lost locally, say from evapotranspiration from growing a crop. Return flows would be the portion of the water that was withdrawn that is returned locally also. So for example, municipal use, we draw water from groundwater or surface water, use the fresh water, and then we might be returning 95% of that water back to the aquatic environment. But there's a twist on these return flows that I think you'll find interesting that we looked at. So now into the methods. How did we calculate these virtual water imports and exports? And so it's really sausage making. We combine, again, different sorts of data sets in order to come up with these imports and exports at the county scale. So let's also I'll start by providing some more water use definitions. So the sources that we looked at were Great Lakes water, so that's the lakes themselves, the tributary surface water, that's the big focus here primarily, and then shallow and deep groundwater. And we distinguish between shallow and deep groundwater because we say that shallow groundwater is connected to the local streams. And that'll become important again in a minute here. Whereas deep groundwater, we assume, is not hydraulically connected to the streams. And just keep that in mind for the moment. So I already mentioned I break withdrawals down into return flows and consumptive use. Then we can take the total consumptive use, and in order to calculate the virtual water exports, we need to split that into water that's exported out of the watershed or the county, and water that stays, that's used but stays to produce something but actually stays within the county or the watershed. And then we have our use sectors. So these are the 6 sectors that we look at. These are sectors that commonly correspond to common use sectors for water use data that's collected by the states in the Great Lakes region. And then another distinction that we make is, I don't know if you're familiar with these concepts of green and blue water. Green water might be, you could think of that as rainfall that's captured and used by the vegetation associated with a particular land use. So forests, of course, use green water, crops use green water, and so forth. As opposed to blue water is water that is physically taken out of a water body and used for, let's say, irrigation. So green water you can think of as sort of free water. It rains anyway, but of course different land uses are going to end up having different amounts of evapotranspiration. Crops versus forests, for example. And again, please stop me if any of these definitions are confusing or you want to quibble with them or anything like that. Okay, so our calculation framework then, the sorts of data we collected was what are classified as large withdrawals in the Great Lakes states, at least the US states, and they're categorized by location. The use category, municipal versus agricultural and so on, and the source from which they draw. And so we had about 7,300 different water withdrawals. This data was obtained from all of the Great Lakes states. which was one of the most time-consuming parts of the project, was to actually get the data and then harmonize it so it was all on the same basis. And then we also need a groundwater model, which I'll tell you about in a couple of slides, that will allocate groundwater withdrawals from shallow aquifers between surface water and groundwater. And then I already mentioned that these are the different water sources we looked at, and then these are the different water use sectors. So sorry if this is kind of confusing, but at the top, this is just a flow diagram showing how water is allocated. So is accounted for. On the top, you see the sources. So we have deep and shallow groundwater, tributary surface water in the Great Lakes. The W just stands for withdrawals. And then those withdrawals are split into consumptive use and into return flows. Just to go through this hopefully pretty quickly, the Great Lakes surface water is withdrawn. Some of it is used consumptively, and there are also return flows that offset that consumptive use. Tributary surface water, which again is our main focus here, results in consumptive use from stream flow and thereby stream flow depletion. Again, some of the withdrawals are returned to the streams. Then shallow groundwater, some of that the pumping from the groundwater results in reduction of groundwater storage, but some of it also results in consumptive use from the stream flow. And again, I'll explain how that occurs in a moment here. So I'm not going to go into too much more detail here, but one other thing I want to mention is that when we use surface water, we return it to that same source usually, right? We take water out. If it's a city, we use it locally. We return it back to the river from which it came. Groundwater, that's not the case, right? We pump groundwater out. We don't return it to the groundwater. We return it to the surface water. So those extra blue lines here are showing that some of the deep groundwater that's used, the return flows from that deep groundwater goes into the stream, and the same with some of the shallow groundwater. Does that make sense? Okay. Yep.
So, the decision part regarding the artificial recharge of groundwater.
You mean when you're doing it purposely to augment the groundwater?
Yes, because that could be another.
Sure. Yeah, that's. I don't think you'll find that in the Great Lakes that we're doing. That I know of, that we're doing any substantial artificial groundwater recharge. But certainly you'd have to have an arrow to account for that if that was going on. Okay, so the surface water groundwater connection. Shallow groundwater aquifers are often connected to local streams. So, whoops. Here's the shallow groundwater. Again, it's often connected hydraulically to the local stream. That's why streams flow in between storm events, right? It's base flow from the groundwater is a term we use for water that flows from groundwater into local streams. If we start pumping, however, if we pump enough, we can actually reverse that flow. So until the well was there, you can see that the head here, or the elevation here of the water table is higher than the stream, which means that all of the water will be going straight into the stream. If we put in a pump and we pump enough, we can actually reverse that in a more extreme case, or at the very least, we're reducing the amount of base flow that normally would be reaching the stream. So this is where groundwater pumping can cause stream depletion because we're intercepting that base flow that should have gone there. And then, of course, we should remember that some of that pumped groundwater is actually returned back to the stream, but the main thing I wanted to illustrate here was this pumping of groundwater affecting streams, local streams. And how do we account for that? Basically through this equation here, which don't worry about all the variables right now, but this equation basically tells us the fraction of the groundwater pumping that's coming from the streams and the fraction that would be coming from the groundwater, depleting the groundwater storage itself. And that depletion is a function of the pumping rate, as you might guess, how far away you are from the stream, some of the aquifer properties like transmissivity and storage, the conductance at the bottom of the stream. And so what we built was a GIS database that would account for the locations of the streams and the wells, the aquifer properties, and we can also account for multiple streams, because you can imagine you have a well between two streams. That well could affect both streams, and the amount that it affects each stream might be an impact, for example, whether it's closer to one or another. Okay, to convert from withdrawals to consumptive use, this is probably one of the biggest problems with doing these sorts of calculations. You need some sort of consumptive use coefficient. And these are the ones that we use from a USGS study of consumptive use coefficients in the Great Lakes region. You see these three different sets of values that we call a low, a medium, or the base case, and high. And you can see those consumptive use coefficients can vary quite a bit just over those ranges. So these coefficients are what you multiply against the withdrawals to find out how much of the withdrawal is consumed locally versus how much is then returned as return flow. So these are really critical numbers. And we're also, our subdivisions of categories are pretty crude, right? We're saying there's one consumptive use coefficient for industry, and that's not going to be the case, right? You know that different industries are going to have different amounts of losses of local losses of water. But this is the data we have at hand. So where does the trade data come from? So we use data from IMPLAN that is a system of input-output trade models, and it provides county-level data for imports and exports for the NAIACS trade sectors, which is a system for accounting for different sorts of industries and so forth in the U.S. And the data also is separated into trade that takes place within the counties, trade that goes in and out, goes to the counties or into the counties from the rest of the U.S., and also it's separated by international trade in and out. So that allows us to look at virtual water trade that stays within a region versus export to the U.S. versus the rest of the world. And the way these input-output tables work is that you have these coefficients here that relate for, let's say, something that's being purchased. You might have these A, B, C, D, F representing different materials maybe you're purchasing. Those go into the input-output table, and what comes out is the amount of material that comes out then on the processing side. The drawback, as I'm learning, is that these coefficients are static, and they don't account for any dynamics that really should be there in an economic model. So we now have to do some data manipulation. So we merge the trade sectors into our 6 water use sectors, the trade data. We say that the county level stream flow depletion is equivalent to the virtual water exports of the stream flow. And then we couple the stream flow depletion data, which again are the exports, using a series of matrix operations. And what we come up with is value intensity. So a value intensity has units of dollars per cubic meter. So let's just look through where that might have come from. So here are the IMPLAN sectors for agriculture. So we merge those IMPLAN agricultural sectors into a single agricultural sector. That gives us the dollars per year being traded, exported, and also imported per year for that sector. Then we also know from our county level withdrawal data the depletions associated with each of those sectors. So this comes from the IMPLAN data, this comes from our withdrawal data set. And we just simply divide this by that, and we have, again, what we call the value intensity. So the dollars of trade that's being produced per cubic meter of water that's of stream depletion or stream consumption. Does that make sense? More or less. Okay. And in this arrow is easy for me to say is a bunch of matrix manipulations. I have the paper. I can show you what those look like. I certainly don't remember them. So one key thing we do next is that we assume that value intensity for the exports is the same as for the imports. So if I'm producing corn in one of the counties in Michigan, I know how much water was used to produce that. I know the export of that corn in terms of dollars out of that county or watershed. But I have no idea if I'm importing corn also where that came from. Certainly you could do the work perhaps to do that. Well, we don't know. And we don't know how much water was used to produce that corn that we might be importing. So we assume that value intensity is the same for that we calculated for the imports is the same for the exports. It's a big assumption, but what it does, it's probably not correct because, again, we have no idea what the irrigation practices are for, or whatever water use practices are for the imports. But what it helps us think about, is that it allows us to treat the imports as offsets of water consumption. So if I'm growing every kilogram of corn that I import, supposedly means I did not have to grow that corn and did not have to use the water to grow that corn. So we think of the imports, again, as sort of offsets of things we don't have to do as, because somebody else had to suffer or whatever producing that, using the water to produce those imported goods. So let's look at some results, first basin-wide. This shows the water withdrawals and depletion, which you can more or less think of consumption right now, for the 4 different sources of water in the Great Lakes. So we have the surface water, again, that's the inland lakes, streams, and so on, deep groundwater versus shallow groundwater, and then the Great Lakes themselves. So the red bar is the orangish bars are the withdrawals, the blue bars are the consumptive use. So this is aggregated over the whole data set. So, and then these percentages are the average consumptive use coefficients. So notice this is a log scale. So for example, on average, 9% of surface water withdrawals are consumed locally, 91%, then 100 minus 9 is returned. We see that the consumptive use coefficients for the groundwater are much higher. And why would that be? So why would it, let's say I'm growing corn with either surface water or groundwater. The consumptive use should be the same no matter what kind of water I use. But why are these groundwater ones so high? Yep.
The water's returning to the surface water, not
Exactly. So the groundwater use is 100% consumptive, really, because from the groundwater's perspective, from the whole hydrologic cycle perspective, it doesn't really matter because someday they'll come back together again, presumably. But this shows we're effectively mining groundwater, sticking it into the surface water and letting it go into the Great Lakes or into the oceans. And believe it or not, some people have actually tried to calculate the amount of sea level rise associated with this water that we're shoving into the oceans. It's very small compared to all the other sources, but it's not completely negligible. And then Great Lakes water is even lower consumptive use coefficient than the others. This is primarily because much of the water that's taken out of the Great Lakes, at least on the US side, is used for thermoelectric power plants or for cities, and they usually have very low consumptive use coefficients. As opposed to the surface water is more, some of it's used for, the inland surface water is used for, quite a bit is used for agriculture. The other things to point out here is these stippled or faded parts here. This is the amount of, over here, this is the amount of surface water depletion that is connected to the groundwater pumping. So if you compare these two things to these two things, what it shows is that this is the effect of the groundwater pumping on the surface water depletion is fairly small, at least on aggregate in the Great Lakes. That's certainly not true if you look at a small enough scale. There certainly are places in Michigan, for example, where over-pumping of groundwater has caused streams to literally dry up. Okay, now getting towards the imports and the exports. So these are gross imports or exports by trade sector, basin-wide, or at least the U.S. portion. I don't know if this is a surprise to anybody, but and again, notice the log scale. The vast majority of imports and exports are associated with industry or commercial, and then much less so on all of these other sectors here. And in all sectors, we see that imports coming into this region are, in some cases, substantially larger than exports. The difference between these bars doesn't look that big, except maybe here and here, but remember, this is a log scale, so these differences actually are quite large. So this is really the key right here. We could almost stop if you simply wanted to answer the question, is the Great Lakes Basin a net virtual importer or exporter? We could almost stop here. We see that it is a net, in terms of net trade, that it is a net importer. And then this is the total across all those sectors for the region, at least the U.S. side, and then the total U.S. And this is just some sort of confirmation that people often use a number that the Great Lakes Basin, at least the U.S. part, provides about a third of the GDP of the United States. And for Canada, it's much larger, right? Pardon? Okay, but I think it's much larger, I believe, because of the concentration of the manufacturing in the basin. So these are these value intensities. Again, notice the units, dollars per cubic meter. So dollars of trade per cubic meters of water consumed from the stream. And we have the 6 sectors here. Again, notice that this is a log scale. And then these are standard deviations, which I know is kind of strange to use when you're talking about log quantities, but these are the more or less the standard deviations across all of the counties. So we see these value intensities vary quite greatly from county to county. So that means that perhaps $1 of one crop relative to the cubic meters that was consumed to produce that crop may be very different depending on what crop you're talking about, let's say within the irrigation sector. So this is getting now sort of to the bottom line here. This is showing stream depletion or stream consumption associated with imports or exports for the 5 different sectors. We see that industry accounts for, if we just focus on exports here, by far the most exports of stream, virtual exports of stream water out of the basin, which is a little bit surprising. You might have thought it was irrigation. And then if we look at imports versus exports, in every case, the imports are higher than the exports. And this is really just related back to this slide here. Again, the imports are much higher than the exports. Notice again, this is a log scale. This is not a log scale, but this difference, for example, between industrial imports versus exports is really related simply to the trade, the difference in trade, difference in exports and imports and exports in terms of dollars of trade. So then looking at it in aggregate, what we're showing here is in units of millions of cubic meters per year, maybe not a unit you're used to thinking about very much, but you can think of these things just relative to each other. 651 million cubic meters per year is traded internally. Okay, so it just more or less stays within the basin. Then imported into the basin, 376 million cubic meters per year versus exported at about 180 to the rest of the United States. And then some substantially smaller amount is either exported to the rest of the world or imported from the rest of the world. Bottom line is right here that the Great Lakes, U.S. side of the Great Lakes, according to our data, is a net virtual water importer, which is, I think, pretty ironic, right? That we sit in the most abundant, supposedly in the place with the most abundant water resources in the world, and we still have to import. So why is that? If you look at the different contributors to imports and exports in the internal trade versus the domestic, meaning the U.S. trade and the international trade, we see that a lot of the internal trade is just commercial to commercial. So we make something in the commercial sector and simply sell it right back within the county or the local watershed. But in the domestic trade, the minuses and plus here is the minus is export and the plus is import. We do export quite a bit of industrial goods, but we also import quite a bit of industrial goods too and agricultural goods. And they come with water. They're coming with virtual water that ends up making the imports substantially greater than the exports. And then international, we export quite a bit of industrial goods, but we also import industrial goods too. So that's the bottom line, I think, is that we look at the region, there's a lot of population here, and we don't make everything, we don't manufacturing everything that we consume in the region. We import a lot of materials, more than we export. And then we have a lot of industry, which of course depends on other industries to produce the parts that go into the things we're making. So the car companies import parts from all over the country, if not all over the world, and those are bringing virtual water imports with them. So let me now go into a little bit more detailed results. So this is just a plot for all of the counties, I think it was 213 counties, where we're plotting the virtual water imports versus the virtual water exports. This dashed line here is the one-to-one line, so if you fell on that line, it means you're importing the same amount that you export. If you fall above the line, it means you're importing more than you export, which we saw in those aggregate data. And most of the points then fall along this is the average ratio of imports to exports. And most of the counties fall on that line, but there are a few that are either substantially above or below. And so the ones that have even higher imports and exports, the counties, are typically ones that are importing more thermoelectric power. So they're getting that water, that virtual water for free because it was being produced elsewhere. Somebody was losing water through the cooling towers somewhere else. And so that is, again, virtual water that's being imported into those counties through the thermoelectric power. And then these other counties on this side of the line, these are ones that tend to export substantially more industrial materials than import. So they're a little bit closer to being, or not a little bit, well, in this case, this county is actually on the one-to-one line. Now, in one of the watersheds, we went into some more detail. This is the Kalamazoo River watershed, which is located right here in southwestern Michigan. And we looked at this one in some detail because Michigan has these stream depletion rules that say this is the maximum amount of water that can be taken from a stream. And that varies geographically because some streams fall into these, for example, cool transitional, large warm. They all have different amounts of allowable stream depletions on a fractional basis. And what the gray shades here indicate how close you are to that maximum threshold. So anything over 1 would mean you've exceeded the threshold. So the very dark colors here, we have sub-watersheds where the threshold is being exceeded substantially. So the virtual water that's being exported out of these sub-watersheds is being exported to the point to where these ecological thresholds are being exceeded. This is all modeling, so of course we really need to go out and look at those streams to see if that's the case, but it does show that there's major water stress, at least in some portions of this watershed. And again, I just made the point that I think that scale matters. This is a frequency distribution for the amount of stream depletion across the whole study area. So what this says essentially is that most of the depletions are very, very small. Don't pay attention to the negative ones. We'll come back to that in a moment. And there are very few that are substantially larger, let's say, than 10% or anything greater than 10%. But we go to a single watershed, the one that I showed before, Kalamazoo River. We have, again, some depletions that are getting 50% or larger. So when we look in aggregate, it looks like we're fine. But when we start breaking down, getting the scale smaller, we see that there's some substantial problems. And now just a couple of things about sensitivity to the formulation of the model and the coefficients. So I mentioned these consumptive use coefficients before. All of the results I was showing you before were for the medium numbers here, or which we call base case. As you might expect, if we look at high and low, we see that the depletions are going to change proportionally. So that's not a surprise. The question is now, which one do you use? Should you be conservative and use the high coefficients or the middle or whatever? And then the last thing is these return flows. So all the calculations I showed you before don't account for these return flows from the groundwater, because that's typically the way these virtual water imports and exports are calculated. So we added in the return flow to groundwater, and what we found is that this is the total depletion over the whole study area without that return flow. When we add in the return flow, we get a negative depletion over the whole study. I know it's hard to wrap your head around a negative depletion. Basically, it's an augmentation. So what this means is that in many watersheds that are depleted because we're taking water directly out of the surface water, or because of our groundwater pumping, we're pulling water from the stream or something like that, that's easily overcome by those return flows. Does this make sense? So all this water we're pumping out of the groundwater, using it, and then returning probably the majority of it and being stuck into the surface water, you could say is making things better. I wouldn't necessarily say that. From our calculations, we have some streams that could be running as much as twice as much flow, even more than that, during certain months because of all this additional water that's actually being stuck into the stream. So it's much more fun maybe to talk about water scarcity when you're on this side of the bar, but in reality maybe it's reverse. It's negative water scarcity, which is an interesting concept. So again, we see this is where we've added in these two lines here that I showed you before on this diagram. So now to summarize, I think the big takeaway message is that the U.S. portion of the Great Lakes is a substantial virtual water importer, and then the use categories of industrial, thermoelectric, and agriculture are probably where we are the reasons why we're substantial virtual water importer. I didn't point this out very well. Maybe I'll just go back real quickly. Well, no, I don't have enough time. In that bar chart I showed you on the value intensities, you may have noticed that the industrial value intensity was substantially higher than many of the others. That's not a surprise, right? That you might guess that on average, every cubic meter we pull out of the ground or the stream and apply to use for industry is going to be more valuable because the dollars created from that industrial good are going to be greater than, let's say, an agricultural good, and we tend to use less water in manufacturing things than we do for growing crops. When we get to the more detailed level, we see that, I didn't show you this data, but the largest imports are usually associated with the thermoelectric sector, And then the largest exports are usually associated with the industrial sector. We also saw that the depletions associated with groundwater withdrawals are really a fairly small fraction of the total stream flow depletions. But then this return flow from groundwater can substantially offset those stream flow depletions. So some next steps. I'm very embarrassed about that blank spot on the map north of the US. So if anybody wants to work together to try to repeat this for Canada, I would love to do that. We also want to look at smaller scales. We're making some headway on that to where we're looking at I showed you the scale issue, right? That you can look on aggregate and say everything is okay, but when you start looking at some watersheds, you see these hot spots. So we're scaling down even more to be able to find those hot spots. Plus, then we can more directly compare to ecological thresholds if we do that. Then we also want to look at both intra and interannual variation in stream flow. For example, we know in most of the watersheds in the US side that August is typically a low flow month. But that's also the time when some of the greatest irrigation takes place. So we might expect to see real severe depletions during summer months. And then also we haven't looked at any sort of interannual variation in trade or water consumption for that matter. Another thing we should look at, I think, is climate variability because, okay, we could look at a low flow month or even a median or something like that. We know that there certainly, there already is a lot of variation and we expect that variation to increase. And then we've been ignoring green water consumption, but I have a colleague who's been doing evapotranspiration calculations that might allow us to incorporate that. And another idea I have is since trade has been a lot in the news lately, and we are including NAFTA, it would be interesting to pick maybe one or two products that go back and forth between our three countries and see how much virtual water is winging its way up and down throughout North America. For example, a car would be a good one to start with. And then the big question, or very big question, is so what? So is there some way that these findings can inform policy? And I'd be happy to hear any suggestions along those lines too. And just some more related work that we've done on looking at groundwater, at water availability and withdrawals in the Great Lakes. And I think that's it.